Okay, Assalamualaikum warahmatullahi wabarakatuh and hi everyone, I'm Sarah. Today I will teach you chapter 5, work, energy and power. Okay, for this chapter we have 3 subtopics. First is work. Okay, for work we need to know the definition of work done, where W equals to F dot S. And next we need to know how to calculate the work done from area under graph F against S. And next subtopic is energy. For energy, you will learn 3 types of energy: UG, US, and kinetic energy. Okay, and for chapter energy, you will learn principal conservation of energy, where summation of energy initial equal to summation of energy final in isolated system. Okay, and for the next subtopic, power, you will learn about power average, where power is equals to rate of work done, and next is power instantaneous, where P instantaneous equals to F dot V. Okay, so now first you need to learn about work. What is the definition of work? Work done is defined as the product of component of the force parallel to the displacement times the displacement of a body. Or work done is defined as a scalar product between force and displacement of a body. Okay, so in equation, work done is equals to F dot S, scalar product or dot product between force and S. Or dot product, if you still remember, in chapter 1, we have learned that dot product is F cos theta times S. Why F cos theta? Okay, let's say we have an object with applied force F and the angle is theta. Okay, and the displacement is to the right. F with angle theta, its displacement is to the right. Okay, we look at the definition. Product of the component of the force parallel. Apa maksud parallel? Parallel adalah selari. Okay, sekarang kita tengok pada gambar rajak ini. Kita nak cari F yang selari dengan S adalah F pada komponen X. How we can resolve F to component X? F cos theta. Okay, that's why the formula for work done is F cos theta times S, where F is force, theta is the angle between F and S is the displacement. Okay, so what is the unit for work done? Okay, F the unit is Newton, S the unit is meter. So, unit for work done is Newton meter, or usually we will use the unit is joule. And work done is a scalar quantity. So, no direction for work done. Okay, other than this formula, we also can determine work done by using, okay, this is the first method to determine work done. The second method to determine work done, we can use area under graph F against displacement. Okay, if we have graph F in Newton, S in meter, okay, S is displacement, and the area under the graph is equal to work done. AUG is area under graph. Okay, there are few cases for work done. For the first case, if we have an object move to the right with external force F and with displacement S also to the right. Okay, we applying the formula for work done. W equals to F cos theta S. Okay, the theta is the angle between F and S, but for this case, theta is 0 because they are parallel. okay, times S. As we know, cos 0 is equals to 1. So this is the maximum work done. Work done is equals to Fs. And for the next case, okay, for example, an object with normal and weight moving to the right. Okay, work done by the normal force. Okay, the formula for work done is F cos theta S. But for this case, the force is normal. So N cos theta S. N cos theta. What is the angle between N and S? The angle between N and S is 90 degree times S. Cos 90 is equal to 0. So work done by normal is 0. Okay, same goes for work done by the weight. Work done by the weight, the angle between weight and S is 90 degree. So cos 90 is 0. Work done by weight also 0. And for the next case, how about if we have more than one force? Okay, for example, F1 is to the right and F2 also to the right. So the object is moving to the right. Okay, to determine work done, okay, total work done, because we have two forces here. Total work done by F1 plus work done by F2. So we need to determine work done by F1 first. F1 cos theta S. And next, work done by force 2. F2 cos theta S. Okay, and you can determine total work done. Or total work done is equals to F1 plus F2 times S. Because cos theta for both force is 0, so it's equals to 1. Okay, but how about if we have two forces with opposite direction? F1 to the right, F2 to the left. That's moving to the right. So total work done is equals to F1 minus F2 times S. Because F1 and F2 opposite direction. For this case, F1 and F2 same direction. And for the next case, if we have an object with force theta from the horizontal and it's moving to the right, how we can determine work done? We still use formula F cos theta times S. So theta, you need to substitute the angle between F and S. Okay, for the next subtopic, energy. Okay, we have three types of energy. Gravitational potential energy. Gravitational potential energy, the symbol is UG. The formula is mgh. It depends on the height. Okay, for example, for an object on the ground and 2 meters from the ground. If the object is on the ground, so no gravitational potential energy. If the object is 2 meters from the ground, so it has gravitational potential energy. But if the object is higher than 2 meters from the ground, the UG also higher. Okay, so it depends on the height of the object. And for elastic potential energy, the symbol is US. It possessed by an elastic object. For example, spring. And the formula is half kx squared. Okay, x is the compression or elongation of a spring. Okay, for example, for a horizontal spring, okay, this is the equilibrium. Okay, when it's compressed, so it has compression X. So it has elastic potential energy. So bila dia ada compression or elongation sahaja, maka dia akan ada elastic potential energy. Okay, untuk yang ini selanjutnya kita akan gunakan Hooke's law juga. F is equals to negative Kx. Okay, and next, kinetic energy. Okay, so symbol kinetic energy is half mv squared. Okay, dia akan wujud bila objek tu moving. For example, a car is static. When the car is static, V0, so no K. But if the car is moving with 3 meter per second, so it has kinetic energy. Okay, and for work energy theorem. Work energy theorem, work done is equals to change of energy. Change of energy. Okay, berapa energy yang kita belajar tadi? 3 kan? Okay, so work done sama ada change of kinetic energy, change of potential energy. Okay, so work done is change of energy. Either it's equal to change of kinetic energy or change of elastic energy. Elastic potential or elastic, work done is equal to change of energy equals to change of kinetic energy equals to potential energy. Either gravitational potential energy or elastic potential energy. Okay, and for subtopic work done, you will learn about principle conservation of energy. Principle conservation of energy states that summation of energy initial is equals to summation of energy final in isolated system. Okay, in isolated system. Okay, for example, the object is thrown upward. Okay, for this state, you just have kinetic energy. Kinetic energy because it's thrown upward, so it has U. So it has kinetic energy. And after it reached the maximum height, when it reached the maximum height, masa kita belajar chapter 2 dulu, when it reached the maximum height, V is equals to 0. So kinetic energy tak ada. Tapi dia ada H, maka dia ada UG. So, tenaga pada point A ni tadi adalah sama pada tenaga pada point B. Tetapi bentuk tenaga dia tidak sama. Pada point A kita ada K, tapi pada point B kita ada UG. Nilai dia sama. Bentuk tenaga tidak sama. Okay, so now try to solve a few equations. Okay, for question 1, figure 2 shows a block of mass 60 kg pulled by a constant force 200 Newton on a smooth surface at an angle 47 degree to the horizontal. If the block moves 50 meter to the horizontal, determine the work done on the block. Okay, so now these are all the information given. The mass of the block is 60 kg. The force is 200 Newton. Theta is 47 degree. And S is 50 meter. Determine the work done. Okay, work done is equals to F cos theta times S. F is 200. Cos, the angle between F and S is 47 degree and times 50. So the answer is 6819.98 joule. Don't forget the unit for work done is joule. Okay. Okay, for the next example, nampak macam sama. but you read the question carefully. Just now, we discussed if the object is on a smooth surface, but now we discuss if the object is on a rough surface. Okay, so F is equal to 200, masih sama macam tadi. But it has the frictional force between the block and the surface is 70 Newton. So, dia ada frictional force 70 Newton. Okay, the displacement still same, 50 meter horizontally, and you need to calculate the net work done. We have two forces here, external force and frictional force. So, for net work done, you need to find the summation work done by the external force plus work done by the frictional force. Okay, first, we need to calculate the work done by the external force, F cos theta times S. F is 200 cos 47 times S is 50. So, work done by the external force is 6819.98 joule. And next, how about work done by the frictional force? We use formula F cos theta times S. F is 70 cos the angle between the displacement. Okay, sebab dia tertarik ke kanan tadi, so displacement ni ke kanan. The angle between frictional force and the displacement is 180 degree and S is equals to 50. So, we will get the answer negative 3,500 joule. Okay, so kita totalkan sahaja 6819.98 tambah negatif 3500. Kena ambil nilai negatif dia. Okay, so the answer is 3319.98 joule. Okay, or you can write 3.32 kilojoule. Okay, sebenarnya kita ada force lain. Kita ada normal juga. Dan kita ada weight juga macam kita belajar chapter 4. Tapi kenapa kita tak tambah work done by normal, work done by weight? Sebenarnya kena tambah. Tapi macam kita dah bincang tadi, work done by normal and work done by the weight is 0 because they are perpendicular to the displacement. Okay, ini contoh kalau kita ada dua force sahaja. Okay, mungkin nanti soalan awak akan jumpa 3 force. Ada lagi satu force yang horizontal, F2 horizontal. So, tambahkan je work done by F2. Okay, contoh. Okay, kita teruskan. Okay, for question 3, figure 2 shows the variation between the applied force and compression of a spring. When the spring is compressed 0.2 meter, calculate the work done on the spring. Okay, as I told you before, work done is also equals to area under graph F against S. Okay, and so for this equation, work done is equals to, okay, you want to determine work done for compression 0.2. So half 0.2 times when 0.2 the force is 8. So, the answer is 0.8 joule. Okay, so done for the work done. Okay, next, for the potential energy of the spring, you want to determine US. Okay, we can use formula half kx squared, but we don't have the value of k. Okay, for this equation, we have two methods to determine US. Okay, first, you can use US equals to half kx squared, where we don't have the value of F. By using Hooke's law, F is equals to negative Ex. Negative just shows the direction is opposite between F and X. For calculation, we can ignore the negative sign. Okay, we refer to the graph. When F is 6, okay, for example, when F is 6, calculate the value of K when the F is 6, the X is 0.15. So you can get K is equals to 40 Newton per meter. Okay, so now you can determine US, half K is 40, X you want to determine at compression 0.2, so you substitute compression 0.2 and you will get US is equals to 0.8 joule. Or the second method, okay, if you still remember, I told you that work energy theorem, work done is equals to change of energy, either kinetic energy, UG or US. So for this case, we can conclude that work done is equals to US. So if you want to determine US is equals to 0.8 joule. Okay, untuk step yang kedua ni awak hanya fahamkan konsep dia. Tak perlu kira pun bila kita dah tahu. By using work energy theorem, work done is equals to elastic potential energy or change elastic potential energy. So US is equals to the work done, 0.8 joule. Okay, for question number 4, we have two masses A and B. We write the mass is given and A and B, and when it push towards each other, okay, push towards each other, the spring is compressed. This is X, 20 cm, and the spring is suddenly released and the object is initially at rest. Okay, mula-mula dia rapatkan, dia pada keadaan rehat, tapi bila dia dilepaskan, it move away from each other. Okay, so ini after that, VA, VB move away to each other. When the spring is no longer in contact with objects, A move away at speed 2 meter per second. So kita ada VA dekat sini. Jadi kita boleh guna principle conservation of momentum. Momentum initial equals to total momentum final. Because of we have two objects, so MAUA plus MBUB equals to MAVA plus MBVB. You need to determine velocity of B. Okay, as we know that the objects are initially at rest. Okay, first, both objects are initially at rest. MA is 1, VA is negative 2. Why negative? Because it's moving to the left. Okay, move away from each other. Plus, MB is 0.5 VB. Okay, calculate. VB is equal to 4 meter per second to the right. Because of the equation asks you the velocity. Velocity is the vector quantity, so you need to state the magnitude 4 meter per second and the direction is to the right. Okay, for the next question, you need to calculate the spring constant K. Okay, as we know that K is, we can determine K by using formula US equals to half Kx squared. Okay, we have K because the spring compressed at 0.2 meter. Okay, but we didn't have the value of US. How we can determine US? We can use principle conservation of energy. Just now we use principle conservation of momentum, but now we use principle conservation of energy. Okay, this is the initial position. Okay, initial, the spring is compressed at 0.2 meter, but the object, both objects are at rest. And after it release, okay, the spring is no longer contact with the objects, but the objects move VA to the left and VB to the right. So at the final position, it has kinetic energy by A and kinetic energy by B. US is 0 because the spring is not compressed anymore. So at the initial position, we just have US. But at the final position, we have kinetic energy by A and kinetic energy by B. Okay, so US is half KX squared equals to half MBA squared plus half MBB squared. Half K is unknown, X is 0.2, half M is 1, VA 2 squared plus half M 0.5, BB just now is 4. Okay, so calculate. Finally, you will get the spring constant is 300 Newton per meter. Okay, for question 5, a 2 kg man starts from rest at A and moving down to B on a 10 meters smooth plane inclined 30 degrees to the horizontal. Calculate the potential energy of the mass at A. Okay, kat sini sebenarnya dia ada height dekat A ni, tapi kita tak diberi height dia berapa. Untuk nak cari potential energy of the mass, kita kena tahulah height A tu berapa, mgh A. Okay, kita tak ada height A, maka kita boleh guna sin theta ataupun sin 30 degree equals to opposite adalah height A over hypotenuse 10 meter, and you will get height A is equals to 5 meter. Okay, so now you can determine the potential energy. Mass is 2, G is 9.81, H is 5. So you will get the answer is 98.1 joule. Okay, next, you need to calculate the linear velocity of the mass just before reaching B. Okay, the linear velocity. Okay, for this equation, we can use summation energy initial or summation energy at A equal to summation energy at B. At A, we have UG. At B, because the height is 0, so it just have K. Okay, UG we have calculated before, 98.1 MVB squared. Okay, we can substitute M is equals to 2, and finally you will get VB is equal to 9.9 meter per second. Okay, next you need to calculate the time taken for the mass to reach at B. Okay, for the mass to reach at B, we can use formula V squared equals to U squared plus 2ES. Just now we have calculated the velocity 9.9, U is 0, 2, we can determine S at displacement 10, so A is equals to 4.9 meter per second squared. Okay, but the question asks you to determine the time taken, so we can use V equals to U plus AT equals to 9.9, U is 0, 4.9 T. T is equals to 2.02 seconds. Or the second method, you can use formula S is equals to half U plus VT, where S is equals to 10, half U0, V 9.9, and T is unknown. And when you calculate the value of T, you still get the same answer. Okay, so we have two methods to determine the time taken. For the first method, we use two equations, but for the second method, we just use one equation. Okay, so that's all from me. Thank you.